very happy to invite the Honorable Professor Dr. Riazuddin for his first lecture. And I will request that if you just come forward because he's going to use the blackboards instead of using the
So this is the introductory lecture on Dirac equation. So let me start by giving you the relativistic notation. And we will put C equal to 1. And then we have this is contravariant vector, then we have corresponding to this one also. So that will be T minus X. So that you will have X mu is T square minus X. So this is the length interval which we will be using. And similarly, let me give you the derivatives which you can write as this one. And the gradient and this one. So that this thing here will be delta square or delta T square minus X square. And also let me introduce the metric tensor also. So we have X mu, X mu, and similarly we can use this one here. And we have G0 equal to 1 and Gij equal to minus 1 if I equal to j and equal to 0. And then we can write our length interval as G mu X mu G mu X mu. Now, having introduced this, now let me say a few words about quantum mechanics. Now, the quantum mechanics is actually based on two basic concepts. One is the concept of dynamical variables. Like momentum, angular momentum, etc. Here we have classical analog. But in quantum mechanics, they are operators. So they have classical analog, but are treated quite differently in quantum mechanics. The second is the concept of state. Now this has no analog, classical analog, but it is essential in quantum mechanics. Because when you have operators, you must have some state to act on them. Okay, so these are the two concepts. This is usually written like this as the state vector in Dirac notation, state function. If you take a particular representation of this one. Now, let me, after introduce this, let us derive the Schrödinger equation. So we start from this classical relation in Newtonian mechanics, and then we treat them as operators. So I am putting X continuity. The gradient of the 2. And you substitute here, you get the free particle Schrodinger equation. And so it has to account some state function. So you have then the free particle Schrodinger equation, and if you put here the potential energy, you can have the Schrodinger equation in the potential with the potential. Now this was the situation in 1928 when quantum mechanics was formulated by Heisenberg using this approach and by Schrodinger. And then Dirac actually also did some fundamental work on that. So at that time, the big problem in 1928 was that this equation is non-relativistic because here the time and space coordinates are treated quite differently. So this does not satisfy the basic ingredient of relativity where the time and space should be treated on the same footing. And so this was a big problem, and then the natural thing was to do is to replace this non-relativistic relation with a relativistic relation. So I do the same thing here. So I get here this equation. And this is known as the Klein-Norton equation. Now this satisfies the basic requirement of relativity because the time and space coordinates are treated on the same footing. However, there is difficulty here. So let me write this equation as and minus plus m squared. Okay, so let us write also with y star so I multiply this by 5 and multiply this by 5 star and subtract. So if I do that, I will get here 5 star delta square delta t square minus chi square plus m square 5 and minus 5 star and minus 5 Now I can write it as delta over t phi star delta phi over delta t minus I get phi star delta t and then I get here del 1 over I and then twice term minus minus 5. So I get the equation of continuity here. So what I get is that delta over delta t rho plus L dot j equals 0, where rho is this in the bracket and j is this thing. Now you see this equation here as plane wave solutions, and which you can write as I e raised to power minus I e t Now if you substitute here rho, so rho will become here, as you can easily see, so rho will become here twice E, it will behave like twice E. Now you see the basic trouble is now here. So if E is greater than 0, rho is positive. If E is less than 0, rho is negative. And since you have here this one, you can have both signs here, the positive and negative energies. So you see, you have two problems here. The problem of the negative energy and the problem of the negative probability. Okay, so these two problems in this equation are tied together. The problem of the negative energy and the probability of the negative probability both go together. So this equation was abandoned actually because of this difficulty. Till Pauli and Weisskopf actually consider this as a field equation where this difficulty does not arise because you have creation and annihilation of particles here. So then actually Dirac came and he actually, so it is important that the two problems are together. So Dirac actually came and he used mathematical sophistication, which I will not do here, and he introduced a new quantities which are known as spinors. And these were quite new because you are familiar with vectors and tensors and scalars. The spinors were completely different which we introduced. But this I am not going to do, but I am giving you a simplified version of the Dirac equation. Now if you look at the difficulty which I have there, you see the main difficulty came because we have time to do it. And it was due to this. But we have to treat it on the same way. So the difficulty can be avoided if we use first order derivative of time. But if you use first order derivative of time, then you have to use first order derivative of space also. So here let me give you an analogy with Maxwell equations. So I will write these equations in free space without any sources. these equations are linear, fully relativistic, linear in time derivatives and also in space derivatives. Now, this is one way of doing electrodynamics. The other way of doing electrodynamics is to introduce the vector potential. Now, the vector potential actually, as you know, these are first order equation. The vector potential is more satisfying the second order. So it is second order, like in the Klein Gordon, which is delta over delta T square. So if you have second order equation, but vector potential has 4 components. E and B together have 6 components. So if you use first order equation, you have to deal with more components. If you deal with the second order equation, you have to deal with the less components. This is an important remark here. So as I said, now let us write down the most linear equation with this in mind, that if you have first order equations, you might expect more components. Okay, so let me write the most general equation, linear in time and space. Plus whenever I have repeated indices, it means summation. Minus n equal to 0. So this is a linear equation both in time and space derivatives. So now, as I said, one should expect that psi has components. And therefore, to take this into account, let me write this equation here. So that psi can have components. So now I want to convert it into a second order equation. So I operate by this one here. By this, that is, I multiply by this on this side. So if I multiply on this, I get various terms. Okay, so let me, some of these terms when you multiply, because I will introduce the negative sign here also. So some of the terms will just cancel out and some of them will remain. Okay, this is easy to see if you multiply this. And if I multiply this, I get delta ml, for example, for the first term here. Then I will have the product of delta by t, delta by delta x. And but delta xi is summed over this. So I have the product here also of the same, but summed over this. And so when I, this is delta by delta. Okay, so if I do that, actually, this is easy to see. So the terms which remain are minus delta m. So this is the term which remains. And this is chronic delta. And this is the term which remains. And the term which also remains is and then we have also here I n beta m and alpha I delta xi, and then finally we have minus m scale beta ml and beta m psi m. Okay, now this is actually okay. It will be like the question. And this is obvious from here because this is delta m here, so this will be delta. So it will be like this one, provided there are some restrictions on. So I can also actually here, you see here, these derivatives are commute, delta x by delta x, and therefore I can symmetrize them and put factor of 1/2 there. So this is what you see. So it will reduce to this one, provided I have the following. So if these conditions are satisfied, then this equation which I wrote down will reduce to this one. Now you see these equations. You see here I have alpha j, and so these are not numbers because actually they are matrices. They are not numbers because these, you see from here, the numbers will commute, but they do not commute. Okay, so these are the numbers, not numbers, but are the, so alphas and betas are not algebraic numbers. represented as n by n matrices. And if I use the matrix multiplication notation, so these the and alpha and beta square. So these are the famous drag matrices just by using this condition. Okay, so these are the matrices, but they satisfy this condition. Then the linear equation which I wrote down in the beginning takes the following. Where these are now the matrices, and therefore psi is a column vector. So if they are n by n matrices, then this will be column vectors. So I can write this equation now as I psi equal to h psi, where h the Hamiltonian is now equal to minus I dot the gradient operator plus and if you want to write it in terms of the momentum operator, so this is a perfectly relativistic equation. You have time and space derivatives linearly coming, and then you have but you have several components here. Psi is not a single one component object, but it is a column matrix. It has well defined transformation properties under Lorentz transformation, which we will see, and which will be different from the vectors. Okay, now since Hamiltonian has to be Hermitian, so if it has to be Hermitian, then alpha and beta must be Hermitian. Now next question is how many components these n are. Okay, this we can show that n has to be even, and this we can easily show because you see these antinodes. So you have this thing here. And first, let me multiply. So I multiply by beta on one side here. Okay, so this becomes beta square. So we have beta square 1. Now let me take the trace of this. Okay, now the trace you can always trace A is trace B. So I can write this as trace of beta square alpha minus and beta square is 1 and there is negative sign, so the trace of alpha is, so it is traceless. Traces. Similarly, you can show in the same topology that the trace of beta is alpha. Okay, and further from this one, this relation also, if you put alpha I equal to 1 and j equal to 1, you can see that similarly for the other components, and similarly beta square. So this is one, and then I have this relation also here. So if I take the determinant of these two matrices, now determinant of two matrices you can always write. Alpha I
minus 1 to the n.
It's
I'm saying minus 1 to the n.
yes, that is what I was going to write. So this will be minus 1 raised to the power n. So minus 1 raised to the power n is equal to 1, and therefore n is equal. Okay, so this much we can see that n is equal. Now let us now see what will be the minimum now. Now you see if n is even, you can say that let us take n equal to which is even. Then you see you have three Pauli matrices, and with the unit matrix they satisfy a complete set here. But then you cannot satisfy this condition here. You cannot satisfy this condition here because beta will be then unit matrix, but beta anti-Q will be there. So this will not do. So then next is n equal to 4. So that is okay. N equal to 4 is the lowest rank possible. Okay, so then I can give the representation of these matrices here. So then alpha I can write as it is a 4x4 matrix, and so this is a particular choice. So I can choose alpha I equal to where sigma I are remission and then beta. So this is one choice here, and these are actually 4x4 matrices, but written in this is 2x2, and you can write it as 4x4 matrix. And then psi 4 component. we have two components. So this particular representation is known as Pauli. Now later on I will use another representation which is called the chiral representation, and that I will introduce later, but the two representations are equivalent because they are related by a similarity transformation. Okay, so that I will do later, and the situation will be quite different when we go to 1 plus 2 dimensions actually. Then we will have two inequivalent representations as when I go to that topic after in my 4th lecture, so that we will see. So next thing is that I have written this equation here. So let me write this equation in manifestly covariant form, because it is not in manifestly covariant form. So let me do that now. The same equation. Okay, the equation which I have written here is that and plus I minus n. Now, if you remember let me write it first in this form. So let me where, as I introduced before, this delta mu was delta over delta x mu, and this was actually delta by delta t, which appear, both of these appear here. Okay, so let me multiply this equation by beta. Okay, so this delta over delta t is delta over delta x, and so I put gamma naught beta is equal to gamma naught, and I put then beta alpha I. Let me write it. So let me therefore put beta alpha I. Now beta and alpha are Hermitian, and you can easily check that gamma is anti-Hermitian. Because if you take the product of these two and these anti-groups, so you can easily check. And also you can check that gamma I square is equal to minus 1 for I equal to 1. Okay, so then you see the relations which I wrote down before, the relationship between alpha alpha I, alpha J, alpha J, alpha I. And these equations. Alpha I. Now they can be put in the compact form now. You can put them in this compact form. It is and then this equation actually takes I so it is a manifestly covariant form now here, and then actually its invariance relative when I introduce the Lorentz transformation it will be useful. So we have this equation here. And this algebra is also known as Clifford algebra, and this is a direct algebra of the gamma matrices. And in the Pauli representation, you will have gamma I, which will be zero, sigma I. And the gamma naught remains. So I also introduce here another matrix which is known as gamma phi. Which is product of all these. Gamma phi is an important matrix which we will see play an important role in when we introduce chirality and chiral transformations. So it can play an important role, and you can easily check that gamma phi is a Vichy. And gamma phi is here. Now, out of these gamma matrices, we can form actually 6 independent orbitals. So let me do that now. We have 16 independent components. And these, let me write here 5. And then independent number of components. One is obviously the matrix 1, so it's 1, and then and then you can also write gamma u. Remember gamma 1 square etc. is minus 1, so let me write this gamma mu with this, that mu is not equal. Because otherwise it is just 1 when gamma 1 square is minus 1 actually. So this is usually also, it has 6 independent components. So this is the one you have the commutator of gamma. And the anti-commutator operator is G linear, as we have seen. So we have 6 components here. Then we can also have gamma mu, gamma mu, gamma lambda, where mu is not equal to mu is not equal to. So then it has just 4 components, and this we can easily show that if this is true, then this combination also will be this one is checked. So this can also be written as pi. And then finally we have gamma pi, which are, so we have altogether 6 components. Now you see, this is, we have this linear equation, time and space. Now one important thing which we will see later on is that the great advantage of the Dirac equation is that the 2 problems which I discussed in the Klein-Gordon, that of the negative energy and the negative probability, they are tied together. In Dirac equation, as we will see, the 2 problems are not tied, so you always have positive probability, as we will see, but there is a problem of negative energy states only. And the problem of negative energy states actually Dirac solved by his whole theory, which we will discuss in my 3rd lecture, and gave actually a new picture of what is known as the vacuum. Now to see the implication, physical implication of Dirac equation, so let me now consider this equation in the presence of electromagnetic field, and then we will see what actually it predicts. Actually, we will see that it predicts 2 very important things, that the electron has a magnetic moment and also a spin, which comes out of the theory, not by putting a hand as in shooting the radiation. So we have this equation, and let me introduce electromagnetism. So that is using the gauge invariant wave. So we replace this by the covariant. And then actually you can write this equation, which I have written here. Okay, as I did when I introduced the Dirac equation, I converted it into a 2nd order equation. So I will convert it now into a 2nd order equation, and therefore I multiply by this. Okay, so you see you have here these, if I write it fully, you have here minus gamma d, and then you get here minus m squared. Psi equal. Now if I use these 2 things, I can express this in terms of these 2 variables, and then what you get is then minus one minus I sigma mu, and you have the d mu. Now you see sigma mu nu is antisymmetric, as we have seen, and therefore if I write this sigma mu d mu d mu, I write as sigma mu nu. Antisymmetric, this will not. So we are left here is with this one here. That becomes I sigma mu 1/2. And the commutator of these two vectors. I should have written here. This is actually not sigma mu. Now this operator here is delta mu plus I equal to, and so you can work it out, this operator. The best thing is to operate it on a function f, and then you can easily see that this is actually, because delta mu commute, so it reduces to actually I e, and a mu also commute, so it reduces to delta mu a mu, and plus I e Okay, you can work it out, and you see that delta mu is just the F mu nu, the electromagnetic field tensor, because you know that F mu nu is delta mu minus delta. So this is the electromagnetic field tensor, and this actually you will see gives you this one here. So if you work it out actually, so this commutator which I have written here, so d mu d is equal to the, you can easily see is I e. So you get this thing here, and finally what we get is then one here. After going through this step, so this equation reduces to them. Plus E over T. Sigma mu F plus okay, so if you compare it with the Klein-Gordon equation, the Klein-Gordon equation is in the values of so this will be d mu du. So this will be the Klein-Gordon equation, in Dirac equation. It is this we will then interpret next time, and it is this term which we will see gives rise to the spin as well as the magnetic moment of the electron, which was actually great triumph of Dirac theory, as we see. The spin coming naturally out of this and with the right factor. You see, in Schrödinger equation you usually put by hand the spin, but then you will like to put, because this is a orbital angular the spin. Naturally, you will say that in Schrödinger equation, I will replace L by S. But it is not L plus S, as you see, it is L plus 1/2. And this is a famous spin anomaly, and this will come out naturally from this equation when I write it fully in terms of the electric and magnetic fields. Okay, so I stop here.
So we thank the professor, Dr. Razuddin, for his very informative and excellent first lecture of this series. And if you have any question, perhaps that can be put later on in the remaining lectures. So this concludes the first session of this lecture series, and we'll go for a cup of tea and then come back just in half an hour, and we'll start for the second lecture of Dr. Kashif Sabi on the electron structure of transport.